everybody say hello, Lacey.
Hi, Lacey.
This is the fun class. I love it. Okay. Yes.
Loser.
Yes. All right. So multiplying. This is easier. This is way easier than adding. Oh, when is multiplying easier than adding? That should be a thing, right? But it is. It is. It's kind of like when you're adding fractions versus multiplying fractions. When you're multiplying fractions, you can do just about whatever you want, right? But when you add fractions, you have to find a common denominator. So it's actually harder, right? Adding is harder than multiplying. So that's the same way in this case. 0, 6. Adding is harder than multiplying. Multiplying is easier. All right, here we go. So independent events. The occurrence of one event does not affect the other. Does not affect the other. In a dependent event, the first event does affect the probability of the other. Okay, so here's my case in point right here. I have a deck of cards. They're a massive deck of cards. These are like huge cards. Huge, okay? Huge cards. Okay, so Craig over here is going to pull a card out. I need to show everybody out. One card. Sorry. Easy. All right.
9 of spades.
He has the 9 of spades, okay? So he picks the 9 of spades. Great. Maybe that's the card that Jet wanted, okay? So I'm going to put it back in, and Jet's gonna pull a little card out, okay? And it's not the 9 of spades. He chose the 5 of clubs, okay? Now, when Craig chose, how many cards did he have to choose from?
52.
52, okay? Then we put it back in, and how many cards did Jet have to choose from?
52.
52. We're going to do it again. Craig's going to choose
Are there
a...
jokers? Because that can be 50.
No, there's no jokers.
It's a 4 diamonds.
Okay, but he's going to keep it. So now, Jet is gypped because he can no longer ever pull out the 4 of diamonds because Craig kept it, right?
Yes.
Okay? So he is gypped because he only has 51 cards to choose from, okay? So, the first time I went through and he put it back, that was independent because it does not matter what card he pulled out because he's putting it back in. Jet could have easily pulled that same card back out. Versus, the second time through, they did not replace it. So, he is gypped. He only has 51 cards to choose from, right? Okay? So, you can put it back in there. That's fine. So, a lot of times you will see these words. Replace. And not replace. And that is the difference between independent and dependent. Okay? Replace versus not replace. Yes? You've seen these before. These are easy problems. Okay? So let's go down to example 3. When you're doing this, you're multiplying, by the way. Multiply. So the probability of one and the probability of the other. Example 3, a coin is tossed and a numbered cube is rolled. You're doing 2 separate things, okay? You're going to take some fraction and you're going to multiply it by some other fraction, okay? And this one is going to be designated as my coin toss, and this one is going to be designated as my cube being rolled, okay? So, coin toss, cube roll. Those are my 2 separate events that are happening, but we're going to multiply them together, okay? What is the probability of the coin landing on tails? Stop. Let's stop reading right now, okay? Coin landing on tails. What's the chances of the coin landing on tails? 1/2, 50%. Let's write it as a fraction just so that we can multiply it easier. So 1 in 2 chance are my chances of it landing on tails. What about rolling a 3?
1 in 6.
1 in 6. And those 2 things are happening together, so I multiply them and I get 1 out of 12. So I have a 1 in 12 chance of...
This isn't right.
Oh my gosh. Don't be like Josh. Don't turn it on the way.
It's not right. I think that it's not.
Don't be like Josh. All right, so I have a 1 in 12 chance of rolling a 3 and flipping a tails. Yes? 1 in 12 chance of both of those things happening together. Yeah? All right, so that was independent. Those 2 things did not matter. One did not invade the other one, right? Yeah. Just because I flip the tails doesn't now mean that I have only 5 sides on my coin or on my dice, right? It doesn't. One doesn't affect the other one, right? So example 4, probability of dependent events. A bag contains 12 red. Oh, we're going to do a list. 12 red, 9 blue, 11 yellow, 8 green, which makes a total of 40. Makes a total of 40, I think. Did I add those right? Yes? 20 here, 20 there. 40? Okay. If 2 marbles are drawn at random and the keywords are not replaced. Not replaced. Okay? What are the chances of blah, blah, blah happening, right? So we're drawing 2 marbles. This is going to be my first draw, and this is going to be my second draw. So, Chances of the first draw being a, what do we want in the first draw?
Red.
Red. I want a red first, and then I want a blue. So second is going to be blue. First is going to be red, second is going to be blue. So what are my chances of it being red?
12 out of 40.
12 out of 40. Okay? And what are my chances of it being blue? How many blue are there?
9 out of 40.
9 out of, I'm not
39.
replacing. I'm not replacing, so there's 39 now instead of 40. 39 out of 9 out of 39. And what am I doing with those two fractions? Multiplying them. Okay, before you multiply, we want to deal with as lowest numbers as possible. So we're going to reduce. And you can only reduce if one is in the numerator and one is in the denominator. So like if 12 and 39, if we had a common factor, we can reduce them, right? What about 9 and 40?
No.
Okay, what about 12 and 40 though?
Yeah.
You can reduce them if they're on top of each other. 12 and 40 will both reduce by 4.
3/10.
So 3 over 10 if I divide both of them by 4, yeah?
Yeah.
Now, what about 9 and 39?
3/13.
Yes, 9, if you divide by 3, that's 3. 39 divided by 3 is 13. Yes? Now I multiply across, so 3 and 33, or 3 and 3, and 10 and 13 makes 9 over 130. So I have a 9 over 130 chance of pulling a red out and then pulling a blue out. Okay? Now, that is not replacing. So not replacing, you subtract 1 from the bottom number, all right? Now, what if I said 2 reds right in a row? The first red would be 12 over 40. The second red would be 11. So you would have to subtract 1 from the top number as well, right? If they're both the same color and you're not replacing, you have to subtract 1 from the top number, okay? Now, I didn't tell the other class this, Marcus, so absorb this information, okay? If I am drawing a red and then another red, that is the same thing as drawing 2 reds at the same time. Does that make sense? Right? A red and then a red is the same thing as drawing 2 reds at the same time, yeah? Or even a red and then a blue. That's the same thing as drawing a red and blue at the same time, right? It doesn't matter. It doesn't matter, okay? All right, so if you pull them out, I think some of the wording in the book asks like, I want to draw 2 reds right in a row. Well, that's just a red and then another red, right? Okay, so you treat them as 2 separate fractions, but 2 reds at the same time is like a red and a red, okay? He's getting tired of me, huh?
Yeah.
See, if I just talk long enough, they go away.
Hey, I did that earlier.
I love it. I love it. Okay, now, conditional probability. Conditional probability. This is where it just gets just ever so slightly harder. Because if you read some of these problems, it's like, ooh, what is going on? But then I'm going to teach you how to do them, and you're like, yes, I know how to do this. Right? Okay, so here is an example. Here is an example of a conditional probability. Okay, there are, how many people in here? 2, 4, 6, 8, 10, 11, 12 including me, yeah? Basketball players. Who are my basketball players?
Oh, yeah.
Basketball? Okay, we're good. Okay, so we are going to do we have any boy basketball? Yeah, great. Okay, we're good. So here's my example. I'm going to make up an example and I'm going to do it over here. So probability of basketball. What I'm going to do is I'm going to say I'm going to choose one of you. And I want to know the chances that I'm going to choose a basketball player. Right? So if I choose Craig, he's a basketball player. That's a good thing. If I choose, I don't know, Jet, I didn't choose a basketball player. Right? So, probability of choosing a basketball player. How many total are there?
5. 12. 11. Yeah, 12. Sorry.
11. Are we including me or not including me?
Yes,
With me, okay. So, there are 12 total with me. Yes? 12 total with me. And how many play basketball? Raise your hand again. 5. 1, 2, 3, 4, 5. So only 5 out of 12 play basketball, yes?
Yeah.
Now, that is just a regular old probability that's easy to do. Now what they're going to do instead is basketball given they are a girl. I want a basketball player given that they are a girl, right?
So, like, that means they are.
Given that they are a girl.
So all 5.
So now, here's how this restricts it, okay? You see this word given in here. This is important. Given, okay? Given. We are only talking talking about who?
The girl.
The girls. We're only talking about the girls. We don't care about boys anymore, sorry. Okay? We're only talking about the girls. So given that they are a girl, all right? Now, we are not talking about all 12 of us. We're only talking about the girls. So we've got 1, 2, 3, 4, 5, including me, 6. 6 girls, okay? Now, my bottom number changes from 12 to 6 because now we're only talking about the girls. Now, of those girls, how many play basketball? Who are the girls that play basketball?
3, 4.
1, 2, 3, 4. There are only 4? Did we say 4 or 3?
4.
4. 4 out of 6. That's how it changes, okay? So conditional probability is changing your bottom number. Changing who your total group is, right? It's like sampling out some people. We're excluding the guys now. We don't care about you anymore, sorry. Okay? So, total number changes from 12 to 6. Okay, so let's do example 5 at the top, right here. At a restaurant, 25% of customers order chili, and 4% of customers order chili and a baked potato. Find the probability that someone who orders chili also orders a baked potato. So, normally, blah, 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 blah. What was that? I did not understand anything that was saying. So, normally we are out of 100%. 100% is our total number, right? That's what we do probabilities, right? 100% is the bottom number, right? But now we're not talking about all 100% of people. Now we are only talking about the chili people. And who are the chili people?
4%. No, 25.
25% are the chili people, okay? Now, given the chili people, how many of those people are also baked potato? So chili and potato. 4%. So it's not 4% out of 100 anymore. It's 4% out of 25. Yeah? So 4 over 25 is
So it's only like
16%. 16%. So that's how that changes. 4, if you do 4 divided by 25 and you calculator, it's 0.16. No. Okay, 4 divided by 25 is 16%, I think. Yep. Yeah.
So it's just 16%.
16%. What? So we're not talking about all 100% anymore. It's not 100%. The bottom number is now 25 because we only care about the chili
So
people.
then you have to
If
take
you order
it.
something other than chili, we don't care about you.
So then you just like go from the bottom number however many times that goes in.
Yeah, right. Look at you go. Okay, now the next one. A two-way frequency table is what this guy is. I love two-way frequency tables. In statistics, we don't call them two-way frequency tables. This is one of my favorite words. What? How do you know that?
Because I was in here earlier.
All right. It's a C word. Two-way frequency table is called a contingency table. Okay? So, I might call them contingency tables, and you're going to go, what the heck is that? A two-way frequency table in stats we call a contingency table. That's kind of a fun word, I think, right? So, there we go. All right, a drug company conducted an experiment to determine the effectiveness of a certain new drug. Okay, so here's what's happening. You have people that you are treating with your drug, and then you have your control group, which are usually given a placebo. Yeah, you know what placebo is?
Fake.
It's a fake pill, right? So they don't know which one they're
Placebo.
getting, yeah? Right? You know what I'm talking about?
Placebo.
You could just take a fake pill. Isn't it like realistic?
Okay?
You don't know it's a
They give you fake pills. Okay, so listen to this. Just put your hand up for a second. Okay? So, here's what they do, all right? I have a room full of people that are all sick, right? And I want to know if my drug helps them. So, what I do is I give some of them my actual pill that's supposed to help, and I give some of them another pill that's basically like sugar water, right, in a pill form, okay? And the reason why I do that is because I don't want you sitting here saying, oh my God, I feel so much better, right? It's like a mental thing. Like you mentally feel like you're getting better, like you're not even being treated. So I want to eliminate the whole mental thing of it and give people a placebo. So you basically try to block out of your mind the fact that you're getting better when you're not, right? Because you don't know if you're given the placebo or given the treatment. Because you would look really stupid if you're like, oh my God, I feel so much better, and then you come to find out you were given like a sugar pill, and then you're like, whatever, right? Okay? It's kind of like, I don't know if it takes birth control or whatever, you know, you have like your 20 some days of like the actual thing, and then like, you have seven days of placebo. It's a placebo placebo pill. The reason why they do that is so that you don't forget to take it.
This is commentary.
Yes.
Jacob Meyer's in there.
Yes, he is.
Jacob, I need you to stop by the office, please.
Okay. So anyway, that's like it's like the same thing, right? Okay. So we have you're given the treatment group. You're given the actual drug, right? The actual thing that's supposed to make it better. And then the control group, you're given them a placebo. Okay. Now, of those two, we had people that actually did get better. These are the people that got better. Their condition improved, and these are the people that stayed sick. Okay. So we treated these people. They actually got better. We treated these people, and they stayed the same. They didn't get better. We didn't treat these people and their condition improved. So maybe they just had a virus that their body got over naturally, right? These are the people that we didn't treat that got sicker.
Just a reminder, we will have a down
Okay.
tomorrow. Teachers, please all have all of your down.
Oh, God. Yuck, 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 yuck. Okay. So now, I want to figure out, almost done, I want to figure out the total number of people that their condition improved. The total number of people that got helped. How many people got helped?
Yeah.
2,800.
2,800. How many people got sick or like stayed sick? 1,200. Okay. Now, how many people total did we treat? These are the treated people.
1,200. Oh,
4,000.
2,000. 2,000. How many people?
2,000.
How many people did we not treat?
2,000.
2,000. Okay. So that's the totals. All right. All right. So now in part A, I'm going to read it to you. Find the probability that test subject's condition improved given that he or she was in the treatment group.
Given.
No. So here's what you do. This is what you do every single time. You look for the word given. Okay? You look for the word given. Now, sometimes it might not be the word given. Sometimes they use the word if instead. But those are the two words you're going to look for. If it's given, it's given. You circle given. Sometimes they'll use the word if though. Okay? So then you look at everything that comes after the given. Given that they were in the treatment group. So now we're not talking about everybody anymore. We're only talking about the treatment group. Okay, so that's my new bottom number. So everything after the given. After given equals new bottom number. So treatment group. Treatment group. How many people were in the treatment group?
2,000.
Total 2,000. Yes. So treatment group is total 2,000. Now, of those people, now we go back before the given. Of those people, we're wanting to know whose condition improved. So of the 2,000 that were treated, how many of those actually improved? 1,600. Then I just reduce and I am done. 16 over 20 is 4/5. Does that make it easier? Okay, second one, part B. Find the probability that a test subject was in the control group given that blah, 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 their condition did not improve. Start with the given. Given is here. Everything after the given. Given that their condition did not improve. We are not talking about everybody. We are only talking about the people whose did not improve. Goes on the bottom. How many people's condition did not improve?
1,200.
Condition does not improve. 1,200 total. That's my total bottom number. Now, of those people, how many were in the, we're looking for, control group? Of those 1,200 people, how many of those were in the control group? 800.
So 2/3.
You're right. 8 divided by 12 is 2/3. Yes?
Actually,
Makes it so much easier when you do it that way. All right, sorry. Your homework is like 9 problems, 8 problems.
8.
Whatever. 9 is your 2 and 6.
Did you say number 6?
2, 4, 6.
Shut the video out. Everybody say bye, Lacey.
Bye, Lacey. She's gonna love our